The last section for college algebra of this semester. You did it. You made it. Section 6.8. In section 6.8, all it is are word problems over exponential growth and decay. So right here, I've kind of given you the basic idea of exponential growth and decay. Just kind of talking about it. I mean, right now, given our current situation with everything that's going on with the coronavirus, this is a perfect example of what exponential growth looks like. It's like it's just like in those movies with zombies and everything like that. The president, you see that meeting, it says, Mr. President, this dot right here represents today. And then all of a sudden he says, here's 2 hours, and the dot's bigger. And then in 3 hours, the dot's even bigger. And then he's like, in 24 hours, Mr. President, this is what happens to the United States. And the whole United States is red. That's kind of like what happened with the coronavirus and everything that's going on right now. Um, is massively out of control and it's spreading exponentially. So that's kind of a great example of exponential growth. Some other examples of exponential growth, like I said, when you see in the movies, zombies. When like when if we were in class, we would kind of simulate a zombie spread and things like that. But like if one person had the zombie virus and then they bit someone, now we've got two, and then those two people go bite someone, now we got four. Those four people go bite someone, and now we got eight, and then eight go bite, and so on and so forth. And it just keeps getting bigger and bigger, and that's exponential growth. Okay. Some other things that kind of have like represent exponential growth. Interest, interest, like, and I'm talking the good kind of interest, although there is bad interest out there. Like when you go and you put money into the bank, like in a savings account or in CDs and things like that, that money is going to grow exponentially because of interest. Okay, it'll be slow at first, but eventually, if you leave it in there long enough, it will take off. It'll get larger and larger and larger. Okay. Some other things like that. When we have objects that appreciate, like for instance, classic cars appreciate in value if they're not used and things like that. Um, so that's kind of an example of exponential growth. Their values uh, get larger and larger and larger over time. The collector's items have that appreciation. With exponential decay, we talk about things like depreciation. So, your new car that you bought the other day, as soon as you drive it off the lot, it's not going to be like a classic car. It's going to depreciate in value. As soon as you drive it off the lot, it's already lost value. Okay. And that value depreciates exponentially over time. The other big one that we talk about with Decay, or actually two of them that we can talk about with Decay, is you can think about, in Marvel Comics, Ant-Man. Ant-Man does an exponential decay where he shrinks really rapidly within a few seconds. That's exponential decay because his size is shrinking down exponentially. And then the one that you'll kind of see within the assignment and things like that, you'll look at carbon dating. Okay, carbon dating lets us figure out how old a fossil is based off of this idea called carbon 14, where it deteriorizes at an exponential rate over time. And as scientists, they have learned what that exponential decay rate is. The other thing I forgot to mention in exponential growth that we'll deal with is populations. Populations are all about exponential growth and things like that. So you'll kind of see those. So let's talk a little bit about what you're seeing here. So right up here, you've got your equation. A of t equals a sub 0 e to the kt. So let's talk a little bit about some things that are in here. So A of t, that's the end result. That tells you how much of your population is there or how much carbon 14 is left, so that's like the answer. But this A sub 0, as it says up here, that is your original amount. It's the starting. That's another way I put it. Starting amount. How much are you putting in the bank into that savings? How many people do we start with in this population? How much carbon 14 do we currently have left? Okay. Or how much carbon 14 do we want to have left? Things like that. Or how much carbon 14 is there? So, I mean, that's kind of the rough idea of your starting point. Okay, it's where you begin with. The E, well, that's the exponential E that we've been talking about. So that's not really a variable, that represents a number. Your K is what tells you about whether this thing is exponential growth or if it is exponential decay. The K determines that. And as you can see right here, it tells you when it is growth and when it is decay. So you are growth when your K is bigger than 0. You are decay when your K is less than 0. So in other words, a positive K, a negative K. Okay? Growth is positive, decay is negative. Makes sense. And T, it's all about time. That's what T is all about. T is all about time. Usually it's in years, but sometimes it can be in months, minutes, things like that, depending on what is being explored in the problem. So we're going to take a look at one problem because all these problems work just like this one. The only difference between one problem and the next is they're going to change the numbers and they might make it decay the next time. Okay? So let's talk about one problem. And that's it. That's 6.8. It really is not hard, I promise you. So your problem's going to be like this, where they're going to have like 5 parts to them. And I think there are 2 or 4 problems in here. It's one or the other. I think you get 2 growth and 2 decay. Either that or it's 1 growth and 1 decay. It's one of those two. I can't remember which. But I promise you it's either 2 or 4. All right. So let's answer the first thing. It says part A, determine the initial amount of bacteria. So here's our equation right here. Remember, the initial amount goes in front of the E. Right there. There's the initial amount. So the answer to part A is 100 bacteria. Or in this one, does it tell us what we're dealing with? How many? Nope, it's just a colony of bacteria. So 100 bacteria. All right. Sometimes it tells us, it might be like in grams or something along those lines. Okay. So we got 100 bacteria. What is the growth rate? The growth rate, that's talking about K. Remember, K is up there by the T. So there is your growth rate, 0.045. Now, it won't mine it. It won't mine it. It might want it as a percent. So if it wants it as a percent, all you got to do is just move the decimal to the right 2 places. So, or we could call this a 4.5% growth rate. So just make sure that you look at it and read it. If it says percent on it, then take that number and move the decimal 2 places to the right. If it doesn't say percent on it, then keep it as the decimal. Okay? So there's the first 2 questions. See, like I said, very, very easy. They're not trying to throw anything too difficult at you. Okay? So now, question number, or C says, what is the population after 5 days? So all they're doing is telling you to take this 5 and put it in where T is, because T is measured in days. Okay? So we're just going to go down here. We're going to say 100 E 0.045 times 5. And we just need to go to our calculator and figure this out. Now, in this one, you're going to have decimals. So make sure that you read the fine print under the box so that you know where to round to. So 100 second E 0.045 5. Okay? And there's how many bacteria we're going to have. And since we're talking about bacteria, I'm going to knock off the decimal and let's say round to the nearest whole number. So we're going to say it's 125. Bacteria. See? Nothing crazy. Pretty easy. All they wanted you to do is plug in. And all these problems are going to follow this same format. So don't let it throw you off, okay? You're all going to be doing the same thing, all right? So moving on to the next one. So this one says, how long will it take for the population to reach 140 grams? See, I knew this was in grams. So this should be probably 100 grams of bacteria, okay? And this should probably be 125 grams of bacteria, okay? Even better than that. So this should be in, let's just put this little, I knew there was something with grams here. Grams, okay. So now for C, sorry, not C, D, we're just going to set that equation we had equal to 140. Or sorry, yeah, equal to 140. So 0.045, and we're looking for T. So all we got to do is get T by itself. So the first thing is, how do I get rid of multiplication? Because you got to get your exponential by itself before we can take an ln of both sides, because that's the only way that we're going to get rid of exponentials. So how do I get rid of multiplication? You got it, divide. So we're going to divide by 100. Okay, so that will give us 1.4 equal to E 0.045 T. Well, how do I get rid of the exponentials? We turned it into logs, which means that we're going to take both sides to an ln. And the ln and the e, remember, they just cancel each other out. So what we have is ln of 1.4 equal to 0.045 t. And how do I get t by itself? How do I get rid of multiplication? Divide. 0.045, 0.045. And now we'll know what t equals. We just got to go to our calculator and take ln of 1.4 divided by 0.045. So alpha y equals ln of 1.4, close it, and on the bottom, 0.045. Enter. And since we're talking about days, they'll probably have you round to the nearest whole, okay? So they probably would say 7, about 7 days. Although me, when I look at this, I mean, we want 140 bacteria. So technically it takes about 7.5 days, 7.5 days. You know, maybe they might want you to round to the nearest 10th. But if we're rounding to the nearest whole, it'd be about 7 days is what it's going to take. Okay? The last problem, part E, is just like this. Okay, it's exactly like this. But instead of 140, it says, what is the doubling time for the population? In other words, they want to know, when is the population double? So remember, our initial population is 100. So we want to double that population. So that means we want our population in the end to be 200. And we set it equal to that 100 E 0.045 T. And we solve it again the same way. Okay, so we'll divide by 100. So that will give you 2 equal to 100, or not 100, excuse me. We got rid of the 100. E 0.045 T. How do I get rid of the exponential? ln both sides. So ln, ln, and we get ln of 2 equal to 0.045 t. Divide by the 0.045 again. And then we'll just go back to our calculator and we'll do the division. And that's all they want in the bottom one is for you to find t again, except this time it said double the population, which means 100 becomes 200. So I'm just going to go right back up, grab that fraction. All I got to do is change that top number there. So we'll delete that piece out, come over here, delete the 1 out. There we go. So it will take us, and again, it'd probably have you round to the nearest whole, so 15, but technically it's about like 15 and a half days. So 15 days. And that's what's going on. That's how you do it. Okay? All these problems are just alike. They ask you about the initial amount, they'll ask you about the growth rate, or it might be decay rate. Then they'll have you plug into T, and then they'll have you do 2 problems where you're actually solving for T. Now, in one of the problems, when it gets into decay, it might ask you what is the half-life. Okay? Half-life means you want half of what is there. Okay? That's what a half-life means. We want half the amount. So if we began with 100, the half-life of 100 would be 50. Okay? So if you see doubling, that means double the initial amount. If you see half-life, that means cut the initial amount in half. But that is 6.8. And there, you're all done. You did it. College algebra, finito.